In the year 2000, the physicist Seth Lloyd published a paper in the journal Nature with a title that sounds like science fiction, Ultimate Physical Limits to Computation. The paper was not science fiction. It was a precise calculation derived from the fundamental laws of quantum mechanics and thermodynamics of the maximum number of operations per second that any physical system can perform. Lloyd did not calculate the limit for silicon chips or quantum computers or any specific technology. He calculated the limit for matter itself. The maximum computational rate of any physical system bounded by the laws of physics, regardless of how the system is built or what it is made of. The number Lloyd arrived at for a 1 kilogram computer operating for 1 second is approximately 10 to the 50 power operations per second, 10 followed by 50 zeros. For comparison, the most powerful supercomputers as of 2024 perform roughly 10 to the 18 operations per second. The physical limit is 32 orders of magnitude beyond our best technology. And then Lloyd extended the calculation to the observable universe itself, treating the entire universe as a computer. The observable universe contains approximately 10 to the 80 atoms and has been running for approximately 13.8 billion years. The maximum number of operations the observable universe could have performed since the Big Bang, given the total energy and the laws of quantum mechanics, is approximately 10 to the 120 operations. Its memory capacity, determined by the holographic bound and the maximum entropy of the observable universe, is approximately 10 to the 90 bits. These are the ultimate physical limits of computation. Not the limits of human engineering, not the limits of any specific technology, the limits set by the laws of physics themselves on how much information can be processed and stored in any physical system of a given mass and energy. I want to take you through what these calculations mean, why they are based on real and well-tested physics rather than speculation, and what it implies about the nature of computation, about the relationship between information and physical reality, and about the deepest question that the computational metaphor raises: is the universe not just like a computer, but actually a computer performing a specific computation that we are part of? Let me start with the foundations of the computational physics that Lloyd drew on, because the specific principles that set the limits are beautiful and important in their own right. The first principle is the Margolus-Levitin theorem, derived by Norman Margolus and Lev Levitin in 1998. The theorem establishes the maximum number of operations per second that a quantum system with a given average energy can perform. Specifically, a quantum system with average energy E can perform at most 2E divided by Planck's constant operations per second. This limit is not a technological limitation. It is a consequence of the time-energy uncertainty principle. In quantum mechanics, a quantum state that has a definite energy E takes at least a time of the order of Planck's constant divided by E to evolve from one orthogonal state to another. Two quantum states are orthogonal when they can be perfectly distinguished by measurement, meaning they carry different information. The time to evolve from one distinguishable state to another is the time to perform one logical operation, one bit flip, one elementary computation. The Margolus-Levitin theorem follows directly for a 1 kilogram mass. The rest mass energy alone is approximately 9 times 10 to the 16th joules, corresponding to a maximum operation rate of roughly 10 to the 50 operations per second. This is the theoretical maximum for 1 kilogram of matter, regardless of what that matter is or how it is arranged. The second principle is the Bekenstein bound, which sets the maximum amount of information that can be stored in a region of space of a given size and energy. The Bekenstein bound says that the information I measured in bits, stored in a sphere of radius r containing total energy E, is bounded by 2 pi times E times r divided by h bar times c times the natural logarithm of 2. For a 1 kilogram mass confined within a radius of 1 meter, the Bekenstein bound gives approximately 10 to the 43 bits. This is the maximum number of bits the system can hold. The Bekenstein bound is closely related to the Bekenstein-Hawking entropy of black holes that I described in the Information Universe video. A black hole is the densest possible storage device allowed by the laws of physics. It saturates the Bekenstein bound. Any attempt to pack more information into a region of space than the Bekenstein bound allows results in the formation of a black hole, because the region becomes so dense that it collapses under its own gravity. Together, the Margolus-Levitin theorem and the Bekenstein bound give the ultimate limits of computation: maximum operations per second, determined by energy; maximum bits, determined by size and energy. Any physical computer, no matter how cleverly engineered, is bounded by these limits. What Lloyd showed in his 2000 paper is that these limits, when applied to the observable universe as a whole, give specific and calculable numbers. The total energy of the observable universe is approximately 10 to the 69 joules, corresponding to a maximum operation rate of approximately 10 to the 120 operations per second times 13.8 billion years. The total maximum information storage is approximately 10 to the 90 bits. The first principle is the Margolus-Levitin theorem, derived by Norman Margolus and Lev Levitin in 1998. The theorem establishes the maximum number of operations per second that a quantum system with a given average energy can perform. Specifically, a quantum system with average energy E can perform at most 2E divided by Planck's constant operations per second. This limit is not a technological limitation, it is a consequence of the time-energy uncertainty principle. In quantum mechanics, the time required for a quantum state to evolve to an orthogonal state, a state distinguishable from the original by measurement, is bounded below by pi times Planck's constant divided by twice the average energy. Two quantum states are orthogonal when they carry different information and can be perfectly distinguished. The time to evolve from one distinguishable state to another defines the minimum time for one logical operation. The time-energy uncertainty principle, in the form relevant here, says that the more energy a system has, the faster it can change state. A system with very little energy changes state very slowly. A system with enormous energy can change state extremely rapidly. The Margolus-Levitin theorem makes this precise. The maximum rate of state change, and therefore the maximum computational speed, is proportional to the energy. For a 1 kilogram mass, the rest mass energy alone is approximately 9 times 10 to the 16th joules, corresponding to a maximum operation rate of roughly 10 to the 50 operations per second. This is the theoretical maximum for 1 kilogram of matter, regardless of what that matter is or how it is arranged. Note that this is the rest mass energy, mc squared. If the matter is also moving or hot, the total energy is higher and the limit is higher. Lloyd's calculation uses the total energy of the system. The second principle is the Bekenstein bound, which sets the maximum amount of information that can be stored in a region of space of a given size and energy. The Bekenstein bound says that the information I stored in a sphere of radius r containing total energy E is bounded by 2 pi times E times r divided by h bar times c times the natural logarithm of 2. For a 1 kilogram mass confined within a radius of 1 meter, the Bekenstein bound gives approximately 10 to the 43 bits. The physical intuition behind the Bekenstein bound is elegant. Information requires physical degrees of freedom to be stored. Physical degrees of freedom require energy to be activated. A degree of freedom with energy less than kT, where T is the temperature, is not thermally accessible. The maximum information storage is therefore determined by how many thermally accessible degrees of freedom fit in a given volume. As you try to pack more information into a fixed volume, you need more energy. Eventually, the energy density becomes high enough that the region collapses into a black hole. The Bekenstein bound is the information storage capacity at the edge of this collapse. The Bekenstein bound is closely related to the Bekenstein-Hawking entropy of black holes that I described in the Information Universe video. A black hole is the densest possible storage device allowed by the laws of physics. It saturates the Bekenstein bound. Its entropy is proportional to the area of its horizon in Planck units. And that entropy represents the maximum information that can be stored in the volume it occupies. Together, the Margolus-Levitin theorem and the Bekenstein bound give the ultimate limits of computation. Maximum operations per second determined by energy, maximum bits determined by size and energy. Any physical computer, no matter how cleverly engineered, is bounded by these limits. What Lloyd showed in his 2000 paper is that these limits, when applied to the observable universe as a whole, give specific and calculable numbers. The total energy of the observable universe is approximately 10 to the 69 joules, corresponding to a maximum total operation count of approximately 10 to the 120 operations over the 13.8 billion year history. The total maximum information storage is approximately 10 to the 90 bits. These numbers have a specific and important implication. The maximum computational capacity of the observable universe is finite, but it is also sufficient to simulate anything we can imagine, including itself. Now let me develop what it means to say the universe is a computer, because this claim can be made in several different senses with very different philosophical implications. The weakest sense in which the universe is a computer is the trivially true observation that physical systems process information. Information is a physical quantity, as Landauer's principle showed in the 1960s when he demonstrated that erasing a bit of information requires dissipating a minimum amount of energy. Physical systems change their states over time, according to the laws of physics. Those state changes can be described as information processing. In this weak sense, everything that happens in the universe is a computation. The falling of a rock, the beating of a heart, the firing of a neuron. This weak sense is not very interesting philosophically. It just says that physics can be described in the language of information theory, which is true but not surprising given that information theory and physics share the same mathematical foundations in entropy and probability. A stronger sense in which the universe might be a computer is the claim that the fundamental laws of physics are themselves computational. This is the position associated with the computer scientist Konrad Zuse, who proposed in 1969 that the universe is a digital computer running on a computational substrate he called Rechnender Raum computing space. It is also the position of Edward Fredkin, and more recently of Stephen Wolfram, who has argued that the universe is governed by a simple computational rule applied repeatedly to a cellular automaton-like substrate. This stronger claim goes beyond saying that physical systems process information. It says that the laws of physics are themselves a computational program, that the universe's evolution is literally the execution of a computation, that the physical world is a specific output of a specific algorithm. Whether this claim is true is an open question. It is not obviously false. Cellular automaton models of physics have been explored seriously by physicists, and some simple cellular automaton rules produce behavior that looks remarkably like physics: wave propagation, particle creation and annihilation, conservation laws. But no cellular automaton model has successfully reproduced the full richness of the Standard Model with its specific particle content and symmetry structure, and it is not clear that any simple computational rule could do so. The strongest sense in which the universe might be a computer is the simulation hypothesis. The universe is literally a simulation being run on a computer outside itself. This is the position explored by Nick Bostrom in his 2003 paper, Are You Living in a Computer Simulation?, which made the trilemma argument that either virtually no civilizations survive to technological maturity, or virtually no mature civilizations choose to run simulations of their history, or we are almost certainly living in a simulation. I want to engage with each of these senses seriously because I think the computational metaphor is one of the most productive and most controversial in contemporary physics and philosophy, and because the specific physical calculations that Seth Lloyd performed connect to all three. The physical limits calculated by Lloyd are relevant to the simulation hypothesis in a specific way. If the universe is a simulation, the computer running the simulation must have more computational capacity than the universe being simulated. The maximum computational capacity of the observable universe is 10 to the 120 operations total. If there is a computer outside the universe running it, that computer must have performed at least 10 to the 120 operations. The computer outside the universe must be at least as powerful as the universe itself, and by the same physical laws that govern the universe, it must be at least as massive and as energetic. This creates an infinite regress problem if you try to take the simulation hypothesis too seriously. The simulator universe must itself be at least as complex as the simulated universe. And if it is physical, it is subject to the same computational limits. To avoid the regress, either the simulator operates with different physical laws that allow more computation per unit energy, or the simulation is not a complete simulation, but only an approximation that looks complete to observers inside it, or the simulation hypothesis is wrong. The last possibility, that the simulation hypothesis is simply wrong, is taken seriously by most physicists. The argument from computational limits is not decisive against the simulation hypothesis, but it does show that the hypothesis is not as easy to accept as it might initially appear. A simulation of a universe with the computational complexity of ours would require a simulating computer of comparable complexity, which raises the question of where that computer came from and why it is not itself simulated. But let me set aside the simulation hypothesis and focus on the more physically grounded question. What does the computational picture of physics, the description of the universe in terms of information processing, tell us about the nature of physical reality? The most important development in this direction is the connection between computation and quantum mechanics. Quantum mechanics is inherently computational. A quantum state is a vector in Hilbert space, a mathematical object that encodes the probabilities of all possible measurement outcomes. The evolution of the quantum state, according to the Schrödinger equation, is a unitary transformation, a specific type of linear transformation that preserves the total probability. Unitary transformations are reversible, which means quantum evolution is reversible, which means it preserves information. This is the connection I described in the Information Universe video. The unitarity of quantum mechanics is precisely the statement that quantum evolution is a reversible computation. The universe's quantum state evolves by performing reversible logical operations on its quantum bits, its qubits. The Schrödinger equation is the universe's program. Quantum computers, the devices that physicists and computer scientists are building today, are designed to harness this computational character of quantum mechanics. A quantum computer manipulates qubits, quantum systems that can exist in superpositions of 0 and 1, performing quantum gates, specific unitary transformations on those qubits. The power of quantum computation comes from the ability to process exponentially many classical states simultaneously through quantum superposition and entanglement. Google's quantum processor Sycamore performed a specific computational task in 200 seconds in 2019 that Google claimed would take the world's best classical supercomputer 10,000 years. This claim has been disputed, and the specific task was carefully chosen to highlight quantum advantage. But the principle is correct. For specific types of problems, quantum computers can be exponentially faster than classical ones. The fundamental reason is that a quantum system with n qubits can exist in a superposition of 2 to the n classical states simultaneously, effectively processing all those states in parallel. For n equals 300, 2 to the 300 is larger than the number of atoms in the observable universe. A quantum computer with 300 qubits, which is within reach of current technology, can in principle process more computational states simultaneously than there are atoms in the universe. This is not magic. It does not mean you can get unlimited information out of a 300 qubit quantum computer. The limitation comes at the measurement stage. When you measure the quantum state, you only get one of the 2 to the 300 possible outcomes, randomly chosen according to the quantum mechanical probabilities. The art of quantum computing is designing algorithms that make the desired answer more probable so that measurement gives a useful result. But the parallelism of quantum computation reflects a deep truth about the relationship between physical reality and information. The universe at the quantum level is not processing one definite classical state. It is processing a superposition of exponentially many states simultaneously. The wave function of the universe encodes all the possible histories, all the possible configurations, weighted by their probability amplitudes. The physical universe is implementing a quantum computation on a scale that dwarfs anything we can build. Now let me take you to the specific calculation that I find most illuminating. What it means that the maximum computational capacity of the universe has a finite, calculable value. The fact that the universe has a finite maximum computational capacity implies that the complexity of any process that has occurred in the universe is bounded. The most complex computation that has ever been performed in the history of the universe, whatever it is, has involved at most 10 to the 120 logical operations. The most complex pattern that has ever existed in the universe, whatever it is, has involved at most 10 to the 90 bits of information. This has a specific implication for questions about consciousness and intelligence. The human brain contains approximately 100 billion neurons, each connected to thousands of others, performing an estimated 10 to the 15 synaptic operations per second. Over a human lifetime of 80 years, the brain performs roughly 10 to the 24 operations. This is an astronomical number by the standards of human-built computers, but it is a tiny fraction of the maximum computational capacity of the universe, which is 10 to the 120. If intelligence can emerge from 10 to the 24 operations in a human lifetime, then systems capable of vastly greater computation could in principle host vastly greater intelligence. The universe's maximum computational capacity is roughly 10 to the 96 times larger than what a human brain performs in a lifetime. What kind of intelligence could emerge from 10 to the 120 operations? This question connects to one of the most profound and least discussed implications of the computational physics framework. If the complexity of a physical system determines the richness of its information processing, and if rich enough information processing gives rise to something like consciousness or experience, then the universe as a whole, with its 10 to the 120 total operations, is engaged in a computation of a richness that utterly dwarfs anything a human mind can contemplate. I do not know whether the universe is conscious. The hard problem of consciousness, which I've discussed in several earlier videos, remains unsolved. We do not understand how or why physical information processing gives rise to subjective experience, even in the case of human brains where we know it does. Extending the question to the universe as a whole is even more speculative, but the computational framework does suggest a specific and interesting way to think about the question. If consciousness requires a certain density or type of information integration, as the integrated information theory of Giulio Tononi suggests, then the relevant question about the universe is not how many operations it has performed, but how those operations are structured, how they are integrated, how information flows through the physical substrate of the universe. A universe that processes 10 to the 120 operations in a completely uncorrelated way, with no integration between distant parts, would not be conscious in any sense we can recognize, regardless of the raw computational capacity. What matters for consciousness, if Tononi's framework is right, is the structure of the computation, not just its scale. The universe's computation is in fact highly structured. The laws of physics are the same everywhere. The forces create correlations between distant parts of the universe through gravity and light. The quantum entanglement structure of the universe connects regions that have interacted in the past. The large-scale structure of galaxies and cosmic filaments reflects a specific computational history, a specific way in which the initial conditions have been processed by the laws of physics over 13.8 billion years. Whether this structure is rich enough to support any form of experience is a question we cannot currently answer. But it is a question that the computational framework of physics makes precise and potentially answerable, rather than leaving it as a purely philosophical speculation. Let me now connect all of this to one of the most active areas of current physics research, which is the question of quantum gravity and space-time from computation. In the Information Universe video, I described the ADS, CFT correspondence, the remarkable result in string theory that equates a theory of quantum gravity in a curved space-time to a quantum field theory without gravity on the boundary of that space-time. The quantum field theory on the boundary can be thought of as a quantum computer. It consists of quantum degrees of freedom performing quantum operations according to specific rules. The gravitational space-time in the bulk is the output of this computation. This means, specifically, that space-time geometry, the physical arena within which everything happens, is a computational output. It is not the fundamental substrate. It is what emerges when you run the boundary quantum field theory computation. Geometry is the readout of the quantum information processing happening on the boundary. This is a profound reversal of the traditional picture. In the traditional picture, space-time is the arena, and matter and quantum fields exist within it. In the ADS CFT picture, the quantum field theory is the fundamental description, and space-time emerges from it. The geometry of space, including its curvature and its topology, is determined by the entanglement structure of the boundary quantum state. If this picture is correct, if it extends beyond the specific ADS CFT setting to more general spacetimes, including our own universe, then the physical world is literally the output of a quantum computation. The computation happens in some more fundamental description that does not have space-time. The space-time we inhabit is the emergent geometry that results from the computation. This is not quite the same as saying the universe is a simulation, because there is no external computer running the simulation. The computation is the universe itself, described in a more fundamental language. The space-time of our experience is the emergent readout of a more fundamental quantum computational process that does not itself exist in space-time. This is the sense in which I think the title of this video is most literally true. The universe is a computer not in the sense that someone built it as a computer, and not just in the trivial sense that physical systems process information, but in the deep structural sense that the fundamental description of reality is quantum computational, and the space-time physics we observe is the emergent output of that computation. Now, let me develop what it means to say the universe is a computer, because this claim can be made in several different senses with very different philosophical implications. The idea that physics and computation are deeply connected has a long history. Alan Turing recognized that any mechanical process following fixed rules is in principle computable, and conversely, that any computable process can be implemented by a physical machine. Richard Feynman, in 1981, asked whether quantum mechanics could be efficiently simulated by a classical computer. His conclusion was no. Classical simulation of quantum systems requires memory that grows exponentially with system size. But a quantum computer itself, a quantum system, could efficiently simulate quantum physics. This launched the field of quantum computing. The universe, being quantum mechanical, is not efficiently simulable by any classical computer smaller than the universe itself. It is trivially simulable by a quantum computer of the same size, which is to say, by itself. The universe is the computer, the program, and the output simultaneously. In quantum computation, a computer consists of qubits, quantum states that are superpositions of classical bit values, and quantum gates, unitary transformations on those qubits. The key advantage over classical computation is that a quantum computer with n qubits can process 2 to the n classical states simultaneously. For n equals 300, that exceeds the number of atoms in the observable universe. The universe at the quantum level is exactly this. Its substrate is the quantum fields filling spacetime. Its memory is the quantum state of those fields. Its operations are the unitary transformations generated by the Hamiltonian. The Schrödinger equation is the program. The evolution from the initial quantum state at the Big Bang to the current quantum state is the computation. This is not a metaphor. It is a precise statement. The Schrödinger equation is a differential equation whose solutions are unitary transformations. Unitary transformations are quantum gates, and the sequence of such transformations since the Big Bang is a quantum computation of specific length. The processing speed of this computation, calculated by Lloyd's methods, is approximately 10 to the 120 operations over the history of the observable universe. The memory capacity is approximately 10 to the 90 bits. These are the specifications of the universe computer derived from the laws of physics. And what is it computing? That question has no answer that physics can currently provide. The universe is evolving according to specific quantum mechanical laws, processing its quantum state from the initial conditions of the Big Bang toward whatever configuration it will eventually reach. Whether this evolution is computing something specific, whether it is an algorithm aimed at a particular output, whether there is a sense in which the computation has a purpose, these questions are beyond the reach of physics. What physics can say is that the computation is happening, that it is bounded by specific physical limits, that it has been running for 13.8 billion years, and that among its outputs is a planet with organisms complex enough to ask the question of what the universe is computing. And what is it computing? That question has no answer that physics can currently provide. The universe is evolving according to specific quantum mechanical laws, processing its quantum state from the initial conditions of the Big Bang toward whatever configuration it will eventually reach. Whether this evolution is computing something specific, whether it is an algorithm aimed at a particular output, whether there is a sense in which the computation has a purpose, these questions are beyond the reach of physics. What physics can say is that the computation is happening, that it is bounded by specific physical limits, that it has been running for 13.8 billion years, and that among its outputs is a planet with organisms complex enough to ask the question of what the universe is computing? Let me now apply the Lloyd limits to the question of artificial intelligence and the future of computation, because this is where the physical limits become most immediately relevant to current concerns. The most powerful current AI systems, large language models, and neural networks with hundreds of billions of parameters perform roughly 10 to the 23 to 10 to the 25 floating point operations per training run. A single inference, one forward pass through a large model, involves roughly 10 to the 12 to 10 to the 13 operations. These numbers are large by historical standards, but small compared to the Lloyd limits. The human brain, with approximately 100 billion neurons and 100 trillion synaptic connections, performs roughly 10 to the 15 operations per second, or approximately 10 to the 24 over a human lifetime. AI training runs are already in this range and will soon exceed it. The question of when AI will surpass human cognitive capability in specific domains is partly a question of computational scale. And the Lloyd limits tell us that the physical limits on that scale are vastly higher than anything we are currently operating at. But computational scale alone does not determine intelligence. The efficiency with which computation produces intelligent behavior depends on the algorithm, the architecture, and perhaps on specific quantum mechanical effects that classical computation cannot replicate. The human brain, with its 10 to the 15 operations per second, outperforms current AI systems at many tasks that require common sense, physical intuition, social understanding, and generalization from sparse data. Whether this reflects a difference in architectural efficiency or a fundamental advantage of biological computation is an active research question. The most extreme scenario allowed by the Lloyd limits would be a computer using all the mass energy of the observable universe, operating at the maximum rate allowed by the Margolus-Levitin theorem for as long as the universe allows. Such a computer would perform 10 to the 120 operations in total. For comparison, the estimated number of computations required to simulate a human brain for 1 second at the neuronal level is roughly 10 to the 15. The ultimate universe computer could simulate the equivalent of 10 to the 105 human brains for 1 second, or 1 human brain for 10 to the 105 seconds, or 10 to the 105 people for the entire history of the universe so far. These are numbers that make the concept of intelligence on a cosmological scale coherent in a physical sense. There is enough computational capacity in the observable universe to support cognitive processes vastly more complex than any biological brain, if that capacity could be organized and directed appropriately. The physical constraints allow for minds of a richness that is difficult to conceive. Whether any such minds will ever exist, whether the universe will ever organize its computational capacity in this way, is a question for the future of intelligence, not the current state of physics. But the fact that the physics allows it, that the Lloyd limits are not a barrier to superintelligence, but rather set its ultimate ceiling at a scale that dwarfs human cognition, is itself a profound and underappreciated implication of the computational physics framework. The universe is a computer. Physics has calculated its processing speed. The answer is 10 to the 120 operations already performed, and the most extraordinary computational fact may not be the scale of the universe's computation, but the fact that a tiny part of that computation has organized itself into observers who can calculate the total. That may be the most extraordinary computational fact of all. If this changed how you think about the relationship between computation and physical reality, tell me in the comments. But before you go, let me sit with the most personal implication of all this, because I think it is the one that matters most. You are a computation, not metaphorically, physically. Your brain is a physical system processing information according to quantum mechanical laws, performing approximately 10 to the 15 operations per second. Your entire lifetime of cognitive experience represents roughly 10 to the 24 operations. Against the universe's 10 to the 120 total operations, you are a tiny fraction of the total. Against the Lloyd limit for 1 kilogram of matter, 10 to the 50 operations per second, your brain is running at roughly 1 part in 10 to the 35 of its theoretical maximum. This inefficiency is not a failure. It is the result of operating in a warm, wet, noisy biological environment where energy constraints, noise tolerance, and evolutionary history have shaped the architecture over billions of years for survival rather than raw computation. The brain is not trying to maximize operations per second. It is trying to navigate a complex physical and social environment, to learn, to predict, to feel, to connect. But the fact that you are doing this at 1 part in 10 to the 35 of the physical limit means there is room for cognitive systems vastly more powerful than the human brain within the same kilogram of matter. The universe has not yet explored most of the computational space available to it within the laws of physics. The organisms that have emerged so far, including humans, occupy a tiny corner of what is physically possible. What would it be like to be a mind operating at a significant fraction of the Lloyd limit? We have no way to know. Our concepts, our intuitions, our experience of time and causation and identity are all shaped by operating at human cognitive speed and scale. A mind operating at 10 to the 50 operations per second would experience the same physics in a completely different way. Time would not feel the same. Computation that takes years of human thought might be accomplished in a microsecond. Problems that seem intractable to human cognition might be solved effortlessly. I raise this not to advocate for the construction of such minds, which raises profound ethical questions I am not going to resolve in this video. I raise it because it illustrates what the Lloyd limits mean for the question of mind and computation. The limits are not a ceiling on what is possible. They are a specification of the full range of what the laws of physics allow. And the range is vast, encompassing everything from the neuron that fired 1 billion years ago in the first nervous system to whatever cognitive systems might emerge over the billions of years the universe has yet to run. The universe is a computer. Physics has calculated its processing speed. The answer is 10 to the 120 operations already performed. And the most extraordinary computational fact may not be the scale of the universe's computation, but the fact that a tiny part of that computation has organized itself into observers who can calculate the total. That may be the most extraordinary computational fact of all. If this changed how you think about the relationship between computation and physical reality, tell me in the comments. Tell me whether you find the idea that space-time emerges from quantum computation compelling or speculative. Tell me whether Seth Lloyd's limits change how you think about the future of artificial intelligence and whether it could ever approach the computational capacity of the universe itself. And tell me whether the universe, being a computer, in whatever sense that phrase is true, changes anything about what it means to be a conscious part of that computation. Subscribe if you want to keep going into the places where the physics and the philosophy and the mathematics of computation all meet.